Hi, we are to build a staircase. And the way it works is that we're getting a number and we have to create a matrix that is this wide and high, and the bottom right, including the diagonal of this matrix, should be the quad character, this little boxy character, and the other one should be spaces. So if we get 5, we need to make this little staircase. And there are a few different ways we can do this. Let's get started. We created a little anonymous lambda. We can always give it a name later. And for now, sure, let's use 5 as example. We need to create something that is the bottom right. So one way we can think of this is it's a range going from the top left to the bottom right. Let's create a range that's iota for its Greek letter like I for indices. The indices up until the argument. The argument is omega because it's on the right and is the rightmost letter of the Greek alphabet. But this only goes in one direction. We need to go 2 directions. So this calls for some kind of table and something that goes diagonally increasing towards the bottom right from the top left is an addition table. So if we create an addition table, we write a jot and a dot, and then with the function we want. This is an outer, like an outer product, but it's an outer addition. And we want to use this iota omega on both sides. So instead of writing it twice, we write the selfie operator, or also known as commute, its official name. And here we can see how it increases towards the bottom right. And once we reach above the number we were given, then that's the parts that we're interested in. So if we compare, if the argument is less than, and then APL will map automatically the single number to all the numbers that are in this table, then we get this Boolean matrix, and APL represents Booleans with zeros and ones. And that's really convenient because since it's just a number, we can add to it in order to get indices. Remember, we're counting from 1, so we generated indices from 1, and we can then use that to index into the space character and the quad character. And then we use square brackets for indexing here. And we've got ourselves a solution. So let's call this one f. And we can apply f. However, if we think about this a little bit, we're doing too much work. We're both doing an addition and then a comparison when we really could just do a comparison from the outset. So if we do an outer comparison table instead, then we do get a triangle. Now this triangle is not right because it's the top right corner and we don't have the diagonal. But the zeros here, they do form kind of a triangle that we want, except it's on the wrong side. So what's the opposite of less than? Well, that's greater than or equal to. Okay, well, we can definitely build on this. The only step that's missing now is reversing. So this, we can see the axis over which we are doing the flip. We're flipping horizontally over that vertical bar, kind of like spinning a globe. And this gives us what we wanted. So if we call this G, and we do the same thing as before, we've got G and apply to 5, and that works. But we can actually do better because let's think about performance here. We are creating a whole Boolean table, and if we were to use a big argument, this table would be rather gigantic, and then we are reversing this entire table. All that's happening here is that we're doing a comparison of the elements going down 1, 2, 3, 4, 5 with the columns 1, 2, 3, 4, 5. If we reversed the columns, so we get 5, 4, 3, 2, 1, then the tall side of the triangle over here would end up on the right. And then it would be created from the outset in the right orientation. So how can we do this? Let's try this. So we've got this outer product, we've got the iota 5, and we've got an iota 5, and all we want to do is reverse the right side like that. But we really don't want to compute iota 5 twice. So what we can do is go back to using this selfie operation, but right before we create the table, we want to pre-process the table function's right argument with a reversal. So jot, in this context, not the same as this one. It has a function on the right and on the left. We essentially apply this function that's on the left, but right before we do that, we pre-process its right argument, so pre-process, with a reversal. And that gives us this table right away, which of course allows us to write a new function that under just the same pattern as before. Oh, G25. I forgot the 1 plus. There we go. Okay. Should we compare the performance of these two? Let's do that. So we copy in the compare execution utility from the defense workspace, and it just takes expressions. So right, CMPX, and then we're running G on say 1000 and G2 on 1000, and then we wait a few seconds for it to run these a lot of times so we get some averaged out results. And we can see that we pretty much halved the runtime simply by reversing arguments to the table generating function instead of reversing the resulting table. Can we do better? Actually, I think we can. Because if you think about it, so let's say with 1000, we generated a table here with 1,000,000 elements, and then we added 1. So that's 1,000,000 additions. But there's maybe something that's worse than that. Today, computation is really fast. What's slow is memory throughput. And APL is clever. It stores arrays generally in the smallest data type, internal data type that it can. So this Boolean matrix is stored as single bits in memory, the smallest units of computation in the computer. Once we add 1, we have to switch to an integer type. And the smallest integers we have available are 8-bit integers, which means we're using 8 times as much memory to store this matrix compared to just storing this. And what can we do about it? Remember that we were counting 1, 2, 3, 4, 5. We're counting from 1. If we switch our system to count from 0 instead, then we don't have to add this 1. We can use the booleans directly to index into this character vector. And over here, what happens is that instead of getting 1, 2, 3, 4, 5, we get 0, 1, 2, 3, 4. They still have the relative size the same to each other, adjacent elements increasing monotonically, and never two elements are the same. So it doesn't really matter what our numbers are in these indices, as long as we're just counting up. So how will this look? And we have a statement separator. Diamonds are unbreakable, so too we can't traverse from one statement to the next one. And in here we're setting a system variable called quad IO. IO doesn't stand for input output, it stands for index origin. So we're setting the system index origin to 0, and it will be local only for this function. And then we can remove this 1 plus. Wonder how big a difference this will make. Look at that. We just halved our runtime again, which means that G3 takes about a quarter of the time with argument 1000 compared to the original G, but pretty much using the same method. Okay, let's look at an altogether different approach. Now we're going to take the quad character and we're going to manipulate it until we get our desired staircase. The way we're going to do this is that we're going to replicate it. So we can write 3 and a slash, that's replicate this, and we get 3 of these. If you write 2, 3, then we can replicate each. So the 2 replicates this, and the 3 replicates it, and we get this list. If we do iota 5, then we get all the components we need for our staircase, but they're, so to say, disassembled. We can assemble them with mix. This increases the rank. The rank of a vector is 1, and we want the rank to be 2. We want it to have 2 dimensions, be a matrix, by breaking this levels of structure. So here's our staircase, and now we can reverse it. But this is not a proper function. We can write it like this. However, I think in this case, the tacit solution, one where we don't mention the arguments explicitly, is a little bit nicer. So this works, but if we use fork constructs, then we can have an array on the left, that's that quad. Then we wanted the replicate each, but now we have swapped the arguments. So this array is on the left and the counts on the right. And for that we use this same symbol as we did before, the selfie, but this time it is used with an argument on the left. So we don't use the right argument also for the left. We use the right argument on the left and the left argument on the right. So it commutes, it switches the argument order. And all we need on the right is the counting up. So the way this works is a tacit function. We don't need the braces. We can put parentheses just to separate it from the argument. Is we apply this function, then we have our array, and then we apply this derived function between the results. This one and, well, its result. It's just a value. So this works. Then we have a mix, which is fine. But we can't just put in a reversal here. This will break the structure because we would have the result of this and the result of this being combined as with being the arguments for this function, which is not what we want. We want these two to be joined into a single function. We could do that with the top operator, which applies this to the result of that and derives a new function. So this works. Now we don't need the parentheses since we're not applying it. Let's call this h. However, we can phrase this a little bit nicer. It's a bit nasty to create this extra level of nesting and then just destroy the level of nesting. We can instead do a mapping of cells in the argument. So over here we have a vector, and its vector is one-dimensional. It consists of numbers that are zero-dimensional. This is itself a zero-dimensional array. It's just a single character. So we can say I want to assemble a new function. I want to assemble a result based on this function. We're creating a new function which is like this one, but maps together arguments of rank 0 from the left and rank 0 from the right. And then take these results so that each one will become a vector, and those vectors have to become the components in our overall result array. So vectors, put them together, make up a matrix. And for that, we don't need a mix anymore. So we don't do the mix here, which means we can just insert the reversal here. Let's call that h2. So now we can do h2 on 5, and this also works. It looks a little bit neater than the original h one we have here. The performance of these two is probably going to be at about the same because the same thing is happening inside. You can try it out though. Yeah, that's within fuzz tolerances. It doesn't really matter. But there's a whole different way we can do this. Instead, both of these solutions, the H solutions, are essentially loopy solutions. We're mapping over explicitly and creating the rows by themselves and then joining them together. Here is a very different way of kind of doing the same thing. And that is by exploiting that replicate, which we saw before, it has some extra tricks up its sleeve. We can do negative numbers, and negative numbers, they create a replication of that element that is the same as the positive value, but instead of using the actual data, the actual value, we're using a prototypical value. And as we saw with the mixing, the prototypical values for this quad character, for any character, is the space, which is exactly what we want. So if you write -2, 3 here, and we only have a single element, we could do an each, but it doesn't matter. Let's do the each just to see how it looks. Then we can see that over here we got 2 spaces and then 3 quads. If we don't do the each, they get joined together. So we get 2 spaces and 3 quads like this. Ooh, but this means we can exploit this. Looking at our staircase, over here we got 4 spaces and 1 quad, 3 spaces and 2 quads. So if we start playing with this a little bit, we've got iota 5, and we want each number to be paired up with, well, with what exactly? Well, first we have a 1, and then we want 4 next to it. So that's 5 minus 1 gives the 4. And the same thing on the next line. We've got 2, we want 3 minus 2. Sorry, 5 minus 2 is 3. But we actually want negative numbers, so we can flip the arguments of those. So let's try this. We do 5 minus this, we get these numbers. If we take this and put the 5 over here on the minus, we get the negative numbers. So now we need to join these pairs together with the original numbers. And there are a few different ways we can do it. I prefer to go directly to a tacit solution. So we've got the numbers from 1 to 5, and over here we have the number 5 itself being passed in. And then we have another function in the middle. We want to subtract. So this gives us our negative numbers. So these are the integers up to 5 minus the 5 itself. This is an identity function. But we don't just want that. We also want the original numbers. So we could get those with the left identity. So this points the finger at this one. And now we just want to combine these two. So we want the minus, and we want the left identity. And we want them concatenated together, but not one after another. We want them to be in 2 columns, in pairs. So we want every scalar from here paired up with every scalar from here. And we did this before with the rank operator. So we want to map over subarrays of rank 0. These are the simple scalars. And that gives us this table. Right. Now we can use this directly, each row, to replicate our quad. We're using the rank again. We need to remember to swap the arguments because we have the array that's being replicated on the left. And this time we want to map over rank 0 on the left and the 1 on the right. But the rank operator actually allows us to remove the 0, because if we ask for something that's higher rank than it has, here rank 1, and it only has rank 0, then we just use the highest rank that we have, which is 0. That gives us our staircase directly. Okay, let's remove the outer parentheses and call this H3. It's the same kind of idea of using replicate, but this time we are forming the pairs that form every vector in itself. So let's compare the execution time of, we know that H1 and H2 are about the same, so we can compare H2 1000 with H3 1000. And that was a pretty significant speed up. Okay, so now we know that, well, we've got the F and we've got the G's. We can actually look at our definitions here. And we know that G3 is the fastest one of the G's, and H3 is the fastest one of the H's. So in order to conserve a bit on space and time, And let's compare the performance of the F and the fastest G. That was G3. And the fastest H. So we have here that G3 is the fastest one. We can see that an F is significantly slower. It would be interesting to run the test again using just G3 and H3, because when something is very much slower than others, it tends to skew the results. Okay, we can see the trend here. And that's it.